Yesterday we are discussing a Redshift architecture. So we said that a Redshift is MPP architecture. MPP means massively parallel processing. So what is MPP and what is SMP? SMP means symmetric multiprocessing, means single node architecture. MPP means massively parallel processing or nothing but multi-node architecture, means multiple nodes will be there. Okay, so in Redshift architecture, okay, there is something called ladder node and the remaining all are compute nodes. So with ladder node, actually it will act as a coordinator. Okay, it will receive requests from the clients. Clients means we are the end users. Okay, so if we submit queries, right? For example, I run query here, select star from employee table. Okay, it will reach to the server. Okay, generally our database is there in the cloud, that is AWS data center. So ladder node will receive that request, and then if it is select statement, it will give to all the compute nodes to retrieve the data. If it's insert statement, then it will distribute the data to all the nodes so that it will be distributed across all the nodes. Okay, if it is select statement, it will retrieve all the data from all the compute nodes and it merges it and gives to the user. And here the point we need to note is that data is distributed across all the nodes. Okay, you can have any number of nodes, okay, based on customer requirement, means based on how much data warehouse he has, so that many nodes he can have it. Okay, so here okay, node will stores metadata, means actually it stores the data dictionary. Data dictionary means like all the tables, information, views of all the objects. It actually knows, okay, what are the tables available in this Redshift. Okay, what are the stored procedures, what are the users. Otherwise, if a user login, it should know, right, whether should I allow this user or no. Or if we are querying a query, it should know that the table is exist. So that's what actually metadata. Metadata means actually data dictionary. Or generally the textbook definition of metadata is it's a data about data. Data about data. But actually it's a data dictionary. It stores or it will have all the information about all the objects that are there in the Redshift server. So yeah, it manages communication with client programs and of course compute nodes. And yeah, it distributes the data to slices on the compute nodes. Please note that when we are saying that is distributed to compute nodes, but actually it is distributed to slices within the compute node. Here we need to know that each compute node will have slices, slices. Okay, so it is that means the data is actually distributed to each slice. Okay, so yeah, those slices will store the data and actually they are the one which will actually process the data. It is something like node is like our body, slices are like our digestion system. Okay, although we eat, we say that we digested the food, but actually who digested the food? Stomach is the one which digested the food. Same thing, and everything will be done by the stomach only, digestion. Okay, and everything. So
if you load it,
yeah, please.
Yes, sir. If you load an employee table, the employee table data will be there in all the slices of the compute nodes. Right?
Yes.
Yeah. So again, when we do a select query on the employee data, then it will go to the all the slices of the compute node and get the data to the leader node.
Yeah, that's right. Right. That's right. Okay.
Yes, sir. Thank you.
Yeah. Yesterday I showed one diagram, right? For example, if you have you see 4 nodes, okay, and you know each node has 2 slices. Then how many slices you have total? You have 4 nodes and each node has 2 slices. Then how many slices you have?
8.
8. Okay. 8. Yeah. For example, you have 80 records in the source. Okay. In the source you have 80 records. Then your 80 records will go to 10 10 10 10 to all the 8 slices.
This will be decided by the leader node, like 10 or 20 or like that.
Not 10 or 20, it will be evenly distributed.
Evenly distributed. Okay.
Yeah, actually there is a separate concept how data will be distributed, but for now in fact it should be easily distributed. You remember that. So you have 4 nodes. Each node has 2 slices. So total you have 8 slices. So if you have 80 records, then each node how many you will get? Yeah. So now you understand how the data will be distributed.
Yes.
Yes, sir.
Yeah. So okay. Now each compute node has how many records? Each compute node.
20.
Yeah, that's right. Because it has 2 slices, so each slice has 10 records, so each node has 20, and you have 4 nodes, so 4 20s are 80. That means actually basically the data is getting distributed to slices. That is the point we need to take care. And yeah, each slice has 10 records, so each slice will manage those 10 records. If you are doing any aggregate like sum of salary, each slice will do sum of salary for the data it has. Like that, 8 slices will work parallelly. It may be sum, min, max, or average, or select, or update. Whatever you do, each slice will do the data that it owns. So that's what actually the parallelism. Basically, this is all distributed systems are basically to have parallelism, because the data is drastically increasing. Okay, so if you just put in single node all the data, it will take a lot of time. But if you have more nodes and each node has multiple processing units like slices here, then data will be quickly done. Each slice will take care. Okay, it don't has to, other data don't has to wait for a single slice. Each slice will do the data processing. That's all, finishes off. So this is all basically targeting towards how quickly we can process the data. So that's where the parallelism is introduced, and this type of architecture is called distributed architecture or MPP architecture. Okay, so basically the funda is that we need to process quickly. Okay, so we are distributing the data, and we have compute units or processing units inside the nodes, and which is processing the data. Bus clear?
Yes, sir.
Yeah. Somnath, you are also clear, right?
Yes, sir.
Okay, cool. So now let me, yeah. So compute nodes, yeah. So basically, compute node execute the query segments in parallel and send the result back to the leader node, yeah, for final aggregation. Yeah. Why leader node has to do aggregation? Because it has to receive everything, and yeah, you should put it one place before giving to the customer, because it's not getting data from single node. It is getting from multiple nodes. So it has to take it and club it and then send it to the user. So that is only we are calling as final aggregation. And yeah, each compute node has its own dedicated CPU memory and a disk. Yeah, of course. Each compute node will have its own resources. So those resources are basically used by the slices. Okay, so
Leader node has to aggregate lot of data. So multiple people using the Redshift, and if the data return is large, so the leader node, is there any scenario, because there is only one node? So is there any scenario of getting issues?
getting
Any issues like any storage limit or any issues, like, because the leader node is a single node and multiple people are querying the data and the result sets are huge that are getting returned. So all the data will be aggregated in leader
no,
node, right?
yeah,
So the
I got your question. I got your question. There is no issues and there is no bottlenecks. Okay, so yeah, only see what it's doing is it's just receiving results from all the compute nodes. Okay, and just sending it. Yeah, of course, that's what we are calling as aggregating. Aggregating means it don't do any processing. All the aggregated data is already came from compute nodes. It just collects it and sends it. Okay, it don't do any processing or anything. Okay,
okay,
yeah,
yeah.
there is no bottleneck.
So leader node size is dependent on the compute node size, like
No, it's not like that. Okay, you will get
what is the
a
configuration
leader
of the
node.
leader node, how it will be decided?
Yeah, so leader node will be given free. Okay, yeah, for example, yeah, it's okay. Anyway, you will get clarity when you create a cluster. Okay, so leader node is nothing to do with compute nodes. Okay, so it comes free. Okay, if you take a single node cluster, it will only that node will act as a ladder and as well as compute. But if you take multi-node cluster, means minimum 2 nodes, you will get ladder node free. Okay, and that later node will be automatically assigned by the AWS. Okay, so yeah, that is that is automatically given. Okay, you will get extra by the AWS. And yeah, that is, we have not seen any time later node getting bottlenecks or anything. Of course, whatever is how many requests we process simultaneously, maybe 1,000, 5,000, 10,000, that is nothing. Okay, with the, if you compare with the processing or compute capacity of these nodes, these are capable of handling millions of records or millions of requests at the same time. Okay,
Yes.
Somnath. Yeah. So actually, which is required more capacity is compute node capacity is required, because that's actually compute nodes are the one which are actually moving the data or processing the data, and we are dealing with huge data in the data warehousing, so, or in the data lake environment. So actually compute node capacity is the main here. So yeah, any delay that happens here only, so we need to take care proper configuration with respect to compute nodes. Okay, so later node, yeah, because it don't do any computing or anything. So yeah, and it is capable of handling even millions of requests at the same time. So yeah, there is no issue at the later node end. Okay, so okay, when coming to the node slices, each slice is allocated a portion of the node's memory and disk space. Yeah, basically slices will present within the node, so they will make use of node resources to do its processing. The slices will work in parallel to complete the operation. Yes, the number of slices per node is determined by the node size of the cluster. I will show you. As I said, right, there are different types of nodes will be there. Each node comes with a certain number of slices. So I will show you now what are different types of slices. Okay, and how many slices you will get with each node. Yeah, because based on node type you will get certain number of slices, and the rows of table are distributed to the node slices. See here, this is the point I'm making. Basically rows are distributed to slices according to the distribution key. Yeah, we will talk about what is this distribution key, or like what is the criteria how the data will be distributed to the slices. Okay, cool. So the last point, Amazon Redshift is based on Postgres SQL, because we know, right? Yeah, it is built on top of the Postgres. Yesterday I said. So it took the Postgres and it made row based storage to columnar, and SMP architecture to MPP, and it introduced some new OLAP functions. So, and it renamed it as the Redshift. So yeah, so basically if you know Postgres, because the base is Postgres, if you know Postgres, you almost know all the SQL of the Redshift. Of course, Postgres is standard. Okay, and SQL. So if you know any SQL, you would be able to know. If you know any SQL, you almost know the SQL of any other database up to 90%. Okay, some extensions will be there. Okay, for any database that you need to know. Similarly, Redshift also some new extensions are there. If you know Postgres, you almost know Redshift. With respect to SQL, but not how the Redshift will process. This processing will be different because its architecture is different. So that's why we're learning the architecture. So yeah, this is the architecture. If you, yeah, definitely will ask, okay, what is the Redshift architecture, or can you please tell me about Redshift? You have to tell all these things. If you don't tell, he will ask you questions. Okay, what is compute node? What is layer node? What is node size? All this stuff he will ask. You should not give that chance. If you don't tell only, he will ask. But when he say architecture, you are supposed to tell all these details. Okay, so you understood, right? This is data warehouse architecture. And the next question is, can you please tell me how the query processing happens in Redshift? That is the next. These two are compulsory questions everybody will ask, or at least we as a Redshift engineer or a database engineer or data warehouse engineer supposed to know. Okay, so how the query processing will happen in Redshift? Okay, so I will tell you what is the concept query processing in Redshift. So as we know, You see, yeah, actually, you see, this is the high level architecture. Okay, data warehouse architecture, high level architecture means client applications will be there. Client applications means end user sitting all over the world. Okay, for example, I will run my query here, but my system or my server is there in AWS data center. Okay, it will go there. Okay, so once it goes to the data center, it will reach to the first. I mean, how I'm connecting to my data center or how I'm connecting to my server. Everyone has to use JDBC, ODBC drivers. Okay, so yeah, that we no need to say. Okay, so once the request reaches to the later node will receive the request and it will perform some tasks. What are those some tasks? What are those some tasks means? For example, I ran some particular query. It should make sure that I, the user, okay, who is logging into the Redshift, has access to those database objects, right? I should have access, right? Otherwise, it should not allow me. Number one, checking access rights. Number two, it should make sure that, for example, I'm querying some finance table or I'm trying to query some payroll table. I should not supposed to have access, right? So, or I'm checking some from some finance table. I should not have access. So, you should check number one, the objects exist. Number two, the user exists. Number three, the user has access to those objects or not. I mean, if object exists and user exists, it does not mean that he will have access. So, it also should check whether this user has access to those objects or not. And once, yeah, all these, I mean, before that, even it should check syntactical errors. Okay, the query that comes is syntactically correct. Okay, so once the syntactically correct, once the user exists, once the object exists, once the user has access to those objects, then it will come up with the best plan how to execute that query, because it already knows where the table exists and how the data is distributed to all the compute nodes and all. So, and it has that information about all the objects in the query. For example, in your query, you have joined some 10 tables. Okay, you have joined some 10 tables. Okay, so in the 10 tables data, it should join. So it should know like what are the big tables, how they are joined, and what case it joined and all. So since it knows all that thing, so it will come up with the best plan. Yeah, it will come up with the best plan. Okay, cool. So that's what we are going to discuss. Query planning and the execution workflow, how it happens. Okay, so yeah, some not all sometimes. Yeah, after architecture question, this is the next question. Can you please tell me how the query processing will happen in Redshift? Okay, cool. So, okay, first a request reaches to the later node. See here, the later node query planning and yeah. So later node first we'll check for or within the later node, it will have something called parser or syntaxer, we call it. Okay, it will check for syntactical errors. Okay, so yeah, the things that I said, syntactical errors and users exist or not, objects exist. Objects means tables, views, whatever you query, a stored procedure, whatever you're running, those are called database objects. So first it will check for syntactical errors, then it will check whether objects exist or not, then it will check whether the user exists or not, then it will check whether the user has access or not. If he has everything, then the request will come to the optimizer. Optimizer will come up with the best plan. Okay, so optimizer means, yeah, so it will come up with the best plan. Why? Because sometimes we query or we run pretty complex queries with 10 tables, 20 tables joining, and each table being a very big table. So at that time it will come up with the best plan for executing that query. Otherwise that query may end up running longer. It may run for 5 hours, 10 hours, but that's not our purpose, right? We want query to be executed as early as possible, if possible less than a minute, less than a minute, if possible less than 2 minutes or 3 minutes, 4 minutes, 5 minutes or 15 minutes. If it is handling too much data, then we may wait till like half an hour or something. I mean, too much data and too complex, but we cannot go on for 5 hours and 6 hours and all, or 8 hours. So sometimes a simple query means not simple query which you generally completes in 2-3 minutes will run for hours together. Okay, so that means there is something wrong, we need to check it and rectify that. Generally this is the problem with the statistics. See here, statistics means I said right, optimizer will come up with the best plan. How can it come up with the best plan? It will come up with the best plan if it knows what are those tables, how big they are, how evenly they are distributed to all the slices. If it has that information, then only it will come up with the best plan. Otherwise it cannot come up with the best plan. So these are called statistics. Statistics means table distribution keys, how many unique rows are there, how big the tables are, means number of rows in the table, okay, and what column the tables will be joined, and how many unique values are there, how many nulls are there, or how many duplicate records are there. All these metrics or values are called statistics. Okay, so all these values if optimizer has, that means if optimizer knows how big the tables are, on what column they are joined, okay, and how many unique values are there in each table, how many duplicates are there, how many null values are there, then it can come up with the best plan. Otherwise it cannot come up with the best plan, and your query may end up running longer. I will tell you, optimizer is like a brain. Okay, it will come up with the best plan. I will tell you how it will come up with the best plan. For example, you are in Hyderabad, or you are in UP. Okay, so you need to go to Hyderabad, but you don't know where is Hyderabad. Okay, so you don't know how much distance it is, you don't know whether it's right, I mean whether it's which direction, you nothing you know. Then how can you reach? I mean, we are human beings, we may ask somebody, but we should not ask. Okay, so we asked you to go to Hyderabad, but how will you? And you are given a car, how will you go? Okay, there is no, don't worry, there is no directions. Okay, on the highway you go Hyderabad, this right left all, nothing like that. So so definitely you cannot go, because you don't know where is the Hyderabad on the map. So you're just roaming with car thinking that Hyderabad will come, and you will go right left center, or just roaming around there. Okay, so but if you are given directions, okay, so I mean you need to go towards this and then take left, then towards right for 10 km, then towards straight on so and so highway, go straight some 200 kilo, something like. If your directions, you can directly go. So the statistics are like that. Okay, how much, how big the table is, on what column it joined, how many unique values are there, how many null values are there, how many duplicates are there. If those values are known to the optimizer, it will come up with the best plan. Then it can execute that query faster. If that values are not known, optimizer will give the wrong plan and your query will run longer. That's why the query which generally completes some 2-3 minutes, sometimes it will run some 10 hours, 15 hours, 16 hours also. So at that time, what is the issue? Statistics are missing. Okay, so we as an engineer at that time immediately realize that are there any statistics up to date or not. So it is our responsibility to update the statistics or to maintain the correct statistics. So then we should check whether the statistics are up to date or not, and then we should refresh the statistics. So as soon as we refresh the statistics, then yes, it will come to know that yes, now it has all the information. Okay, how big the tables are. Okay, how many unique values are there, how many nulls are there, how many duplicates are there, how the tables are joined. So now it can, I mean, come up with the best plan. So it can complete faster. So that means if a job is running longer, that means there is some issue with the job. So even if it is running for 12 hours or 15 hours, it's no meaning keeping it running, because it's not completed for 15 hours. How can you expect that it will complete in another 10 minutes or 5 minutes or 1 hour? So better you abort it and troubleshoot what is the issue. Generally we should check the statistics. Okay, then identify what is the problem, then refresh the statistics and restart it. Then if it is issue with the statistics, it will complete in its normal time as it was earlier. Yeah, so yeah, optimizer has it plays such a major role. So don't worry, there is a separate concept that we will be discussing about statistics. What is the statistics? Okay, how to refresh them, how to check whether the stats are available or not. So we will be checking it separately. So for now, optimizer will come up with the best plan. Okay, once the query is syntactically evaluated. That means parser is the one which parser or syntaxer, it will check for all the syntactical errors and access rights and all. Then it will come to the optimizer. Optimizer will come up with the best plan, and then it will redirect that query to execution engine. Okay, execution engine means query plan sent to the execution engine. Execution engine means, yeah, it is the it's the processor we said, right? Processor. Okay, so then all the steps will be directed to compute nodes, and compute node is the one which actually within the compute node, which one the slices will actually process your data, whatever the query it may be. Okay, so yeah, so what we should do is how the query will be processed in Redshift means, yeah, as soon as the user submit a query will first reach to the ladder node. Okay, so ladder node will receive the request, and within the ladder node there is a parser will check for syntactical errors, and if the query is syntactically correct, it will check whether all the objects are exist or not, and the user has access to those objects or not. Once the valid user is valid and it has access to the objects, then it will send those to the optimizer. Optimizer will come up with the best plan based on the available statistics. Okay, so then it will send those steps to the compute nodes for the processing. Okay, so actually optimizer will split that query into segments. Actually, I mean, segments means small chunks. Okay, and it will send those. I mean, you don't need to tell, or you can tell. Optimizer will split those query to, because your data is there across compute nodes, right? So it will split that query and then give those steps to compute nodes. So all the compute nodes will execute that whatever small pieces and process the data and then give the result back to the, I mean, actually again it will come back through optimizer and through optimizer means it all there in the ladder node only, right? So we don't say optimizer and all. Compute nodes will process the data and give to the ladder node will give to the customer or client. Is it clear?
Yes.
Yes, sir.
So why it is
Okay,
written front end, back end? Like that is something we can see front end.
sorry.
So it is written front end and back end, right? So I just wanted to check whether this is something we can visualize in the UI. This parser,
No,
logical transformation,
no, no,
planning.
this is all internal things, nothing will be visible to you.
Okay.
Okay, this is only we are learning how Redshift work internally when you run a query. Okay,
Yes,
so
sir.
yeah, very important architecture and query planning and execution, or generally how the query will be processed. Okay, or how the Redshift will process your query. Okay, so now I will tell you one more thing. So very important thing that we need to understand while working with the distributed systems or MPP architecture is that what is the difference between traditional databases and these latest coming architectures. These are all based on MPP. You take any cloud architectures or any cloud data warehouse, these are all MPP. MPP means, yeah, the distributed systems. So they all will be in MPP. MPP means what? What is MPP?
Massive parallel.
Massively parallel processing.
Yeah. So that means what? That is abbreviation. That's fine. But what is my MPP?
Distributed processing. Each node will have its.
You will have multiple nodes, bus. Okay. In MPP system, yeah, you will have multiple nodes, right?
Yes,
Yes.
sir.
Yeah. So these are all multiple nodes. and in each node you will have what will be there in the node.
Number of slices.
Yeah, slices. Okay, these are all slices. Okay, I have 4 nodes and each node has 2 slices. So I have I have some 100 records. I mean, it's not 100, it's 100 million records. Okay. So I have 100 million records, and I need to distribute that 100 million records to, for example, okay, I'll tell you one more thing. I have only one, okay, I have only one system. Okay, I have only one node, that SMP architecture. Okay, this is my system. Okay, SMP architecture. So all that 100 million records should go to this particular node only. Okay, so let's say each record loading will take 1 second. Okay, then 100 million records will go in how much time into this single node?
100 million.
Hello. Yeah, 100 million seconds. Okay, so that means if one record will go in 1 second, 100 million records will go in 100 million seconds. So how much time it takes? So total time it takes is 100 million second. Okay, so seconds to hour. So 100 million second, right? So 100 million. You know what is million? This is 10 million. Put comma for every 3 digits. Okay, so after 6 zeros, it's 100 million. Okay, that means this much time. Okay, these many hours. Let's say I said one record will take 1 second. Okay, let's say one record will take 1 millisecond. Okay, I'm giving you one record loading will take 1 millisecond. 1 millisecond means what is millisecond? 1000 of 1 second. 1000. Okay, 1000 part of 1 second is millisecond. So you have 100 million records, and each record will take, let's say, 1 millisecond. Then 100 million records will take 27 hours. But this is also too high. So yes, obviously, if you have 100 million records, it will be like this only. So what we did is, or what the people did is, okay, so because the data is increasing, because they never expected 100 million records in some long old years or some many years ago. Okay, so but 100 millions are nothing nowadays. So the SMP systems are not working because they are not able to provide proper performance, because it's taking hours and hours together. So they have come up with this distributed architecture. Distributed architecture means this one. This is SMP architecture. Okay, so this is SMP architecture. So you will have multiple nodes. I mean, not SMP, MPP. So what is MPP? Massively parallel processing means multi-node architecture, you can say. Okay, multiple nodes will be there, and yeah, each node will have its own processing units. So these are actually slices we are calling, but they are actually the processing units within the each node. So now it has how many nodes? 4 nodes, and each node has how many slices? Two slices. So total it has 8 slices. So now your data, we said right here, in one record will take 1 millisecond. Okay, one record will take 1 millisecond. So in 1 millisecond here, 1 millisecond, you know how many records will go inside?
8.
Yeah, 8. Okay, because now the data will be distributed to all the slices. We say data will be distributed to nodes, but actually it is distributed to the slices. So since you have 8 slices, so in 1 millisecond itself all 8 records will go. So 1 2 3 4 5 6 7 8. Similarly, in next millisecond 8 more, in next millisecond 8 more, next millisecond 8 more. Okay, so like that, these 100 million records will have 25 million in node 1, and 25 million in node 2, 25 million in node 3, and 25 million in node 4. So okay, I said node wise, but actually here it will be something like, you know, 12,500, 12.5 million, and 12.5 million. Okay, so like that. So every slice will have 12.5 million, 12.5 million. So 12.5 plus 12.5, how many? 25 million.
25.
Yeah. So similarly, it also has 12.5. It also has 12.5. So like that. So total, all your 100 million records are distributed to 4 nodes. I mean, 4 nodes means actually 8 slices. So because in 1 millisecond, 8 records got distributed. So within, how much can you, anyone tell me how much time it will take to distribute 100 million records into 8 slices? Hello, I asked a question. Can you please tell me 100 million records will take how much time to distribute into 4 nodes or 8 slices? Actually 8 slices. Yeah. Here you see
Around
here.
7 hours. Or let me
No,
just check.
forget about time. No. Tell me in milliseconds.
Milliseconds.
Yeah. Or not in milliseconds. Tell me in millions or millions or yeah. You see, one record will take, you know, 1 millisecond, right? So 100 million will take how many milliseconds to distribute? You see, 12. You see, total. You see, one time 8 records will go. Two time 8. I mean, in second millisecond 8 records will go. In third millisecond 8 records will go. Like that, you will have, okay, 12.5 million milliseconds it will take. Understood?
Yeah.
Total. These are all 12.5, right? That means 12.5,
Yes,
12.5, 12. So total how many? 100 million, right?
yes. 100 million
Yeah,
milliseconds divided by 8.
8. Yeah, so 12.5 million milliseconds it will take.
Seconds.
You got it, Somnath?
Yes.
Yeah. So I will make it simple. That's why I already took. Okay, let's say it take 100. Okay. Yeah, 100 seconds. Okay, it will take 100 seconds to load it into single node. Okay, and each node or each record will take 1 second to load. Then 100 records will take 100 seconds. Okay, forget about million and all. Okay, 100 records I have, and I have one SMP system, and each record will take 1 second. Then total how much time it will take? 100 seconds, right, to load it into single node. Yes or no?
Yes, sir.
Yeah. Now the same 100 records. Okay, so it will be, we need to load it into 8 slices. So in first second 8 records will go, second 8 records will go, like that. In 12 seconds 96 records
12.5
will go.
seconds.
No, it will not be something. There is no nothing like 12.5. In 12 seconds 96 records will go. In 13 second remaining 4 records will go. Okay, so at that time, you know how the data distribution will be. See here, first 1 1 1 1, like 8, 16, 24, 32, like that, right? So 40, 48, 56, 64, 72, 80, 86. Okay, like that. So total, so 12 12 12 12 will be distributed, okay, in 12 seconds. Okay, so in 12 seconds, 12 records means 12 for all the slices. Okay, so 12. Okay, so you see 12 12. Hello boss, 12 12, each slice 12 12. Okay, okay, so total how many 12s? 8 12s, right? How much 8 12s?
96.
Yeah,
96, sir.
so in 12 seconds 96 records got distributed. In 13 second, okay, how many records are left from the source?
4.
Yeah,
4 records.
so yeah, so it will give that to here. I mean, first 4 slices. Okay, so one more record it will put here. 1 1 1 1. But because there is no more record, so these slices in last 4 slices will be, I mean, there is no. So total how much time it took? Tell me, to load into 100 records into the system.
13 seconds.
Yeah, Somnath, can you tell me?
Yeah, 13, sir.
Yeah, right. So it took 13 seconds. But whereas in the first case, it took 100 seconds, right? In case of SMP system.
Yes.
Yes or no?
Yes, sir. Yes, sir.
Yeah. So that is the benefit of distributed systems. So in earlier case, because there is only single node, so it took 100 seconds. But when we use distributed system, okay, with multiple nodes and multiple slices, it just completed in 13 seconds. Okay, cool. So this is the case. This is the case. Here you see the data is evenly distributed. Okay, so 12 12 12 12 12. Of course, since 4 extra is there, so next second we got consumed. In that 13 second, only node 1 and node 2 got distributed, node 3 and node 4, because there is no data, so there is nothing to distribute here. So at the time they are idle. Okay, that's fine. Okay, only 1 second. So total time taken is 13 seconds. Fine. Now think about a scenario. Okay. So I have 100 records. Okay. But my records are distributed like this. 75. Okay. 5. 5. 5. Total 80, 90. Okay. Something like 3, 3, 2, 2. Okay. How many records? 75 plus 5, 80, 90, 96, 100. You got my point? Okay. So this is also MPP architecture. Okay. So I same 100 records I distributed to. I distributed means the optimizer distributed like this. 75, 5, 5, 5, 3, 3, 2, 2. You understand what I said till now?
Yes.
Yeah.
Yes.
So now the same thing. I have source 100 records. Okay. And to load one to load. For example, you see, to load into one node, how much time it will take to load into single node system? You see 100 records, you need to load into single node system. How much time we said?
100 seconds.
100
Yeah.
seconds.
So 100 seconds. So 100 seconds. Okay, cool. But yeah, we know that distributed systems is so powerful. Okay, we'll get a lot of performance, and we have the 4-node system and 8 slices, and our data got distributed like this. Okay, so we have 4 nodes, and each node has 2 slices. So these are all slice 1, slice 2, slice 3, slice 4, slice 5, slice 6, slice 7, slice 8. Okay, so 75, 5, 5, 5, 3, 3, 2, 2. Okay, like that data got distributed. And same thing, one record to distribute it will take 1 second. Okay, so then can you please tell me 100 records? Yeah, they are distributed like this. Okay, now how much time it will take to distribute like this? Or let us say the data is already distributed like this. Okay, you are selecting from a table. How much time it will take to retrieve the data if it is distributed like this?
75 seconds.
How much?
75 seconds.
Yeah, that's right. Prasad, tell me how much time it will take if it has to distribute like this, or the data is already distributed and you have to retrieve the data from the system. How much time it will take?
75 seconds.
You know how? No, or don't know.
Don't know, sir.
Okay. Somnath, can you tell me?
Yes, sir. So the first node, even if the other nodes contain less data, so in terms of data operation, first node will have 75 times. So the other nodes will be idle in that time. But yeah, so in order to
That's all.
process to come.
Very simple. Yes, yes, yes. Very simple logic, boss. See, we know that one second will take to load the data. Similarly, let's say your data is loaded like this, and similarly it will take 1 second to retrieve the data. Let's say now we are working on a retrieve operation, means you have issued a select statement, okay, and yeah, you need to retrieve the data which is distributed. Like, okay, in first second what happens, all the slices will give 1 record, so eight slices will give eight records. In next second similarly, yes, all the 8 slices will give 1. So for third second, actually you see the node 4 data will be actually 0. It already given all the 2, so it's 0, so it will be idle from third second. So in third second, yeah, so these slices have data, so the first 3 slices has the, I mean the first 3 nodes have data, so it will give. So third second you will get yeah, 1 2 3 4 5 6 records you will get. In fourth second you
Six
will get
records.
again 1 2 3 4 5 6 records you will get.
Six records.
From fifth second onwards,
Four records.
even this node
Four
also
records.
idle, this node also has 0. So now these 2 nodes will be idle, sitting idle, right? From, yeah,
Yes,
from
sir.
fourth, yeah, from fourth second onwards. So
Yes.
only these 2. So up to 5 seconds or up to 5 records, even this node also will start giving data because it has 5. So from fifth second onwards, you see even this slice also will give up to 5 seconds. Is from sixth second onwards, only this particular slice will work. Remaining all already idle, they are 0, right? Right?
Yes, sir.
In 5 seconds, you see in 5 seconds, how many records you got? Here, from here 5, here 5, 5, 5, 20, plus you work 10, 30. Okay, 5, 5, 10, 20, 20, plus 10, 30. Okay, so here out of 75 only 5 has come. So remaining 70 is there. So it will take 70 more seconds to give these 70 records, right? So already 5 seconds only we spent, 5 seconds plus 70. So actually very common is the slice which has maximum data, it will take that many seconds, because we already given one record will take 1 second. So in first few seconds all others will already given data, so they will become idle. Okay, after 5 seconds, I mean this will become after 2 seconds idle, this will become after 3 seconds idle, this will become after 5 seconds idle. Even this slice also will become idle after 5 seconds. So after only this only particular slice will start giving data for one record for every second, one record every second, like that. So total, since it has 75 records, so it will only will take 75 seconds, because meanwhile all others are already given data and they become idle. So here my point is, it will take 75 seconds to give the same 100 records. Then where is the parallelism? In one node you got 100 seconds here in SMP architecture, here you got 75 seconds. So what is the use? Then what is the use of your distributed system? Okay, but in the earlier case we saw only 13 seconds in earlier case, but now it became 75 seconds. Why it became 75 seconds now, but in earlier case it is 13 seconds? Any reason? Hello?
Because data was not distributed properly.
Yeah, simple. Because data is not distributed evenly or properly. Properly is the right answer. Yeah, why? Properly means what? What does it mean properly? Properly means evenly. Okay. Somnath, can you hear me?
Yes, I can hear it.
Yeah. So if you don't evenly distribute the data, even distributed systems is also no use. Okay, the purpose or the concept of distribution system is that so that we will distribute evenly, because by distributing evenly only you will have the best performance. Even after having distributed systems, if you dump all the data in single node or single slice, then it's nothing but the same SMP system. What is the use? No use. Now we saw earlier it was 100 seconds, now it's 75 seconds. What is the use? But if it is evenly distributed, it completed in just 13 seconds, right? So data distribution is very important. That is the point. You understood?
Yes, sir.
Somna, you
Yes.
understood?
Yes.
Yeah. So the next, so the most precaution need to be taken care how your data will be distributed. So the more evenly data is distributed, the more performance you will have. Okay. So the next question, or here one term I need to tell. This uneven distribution of data is called skew. I mean, this is technical term we use in our in distributed systems or in data warehousing area. Skew. What is skew? Uneven distribution of data across all the slices is called skew. Okay, we say more skew. Means if some slices has more data, some slices has less data, means that this particular table has skew, we will say. But if the table, if it is evenly distributed, okay, let's say 12 12 12 12 12 12, or even you see, 13 13 12 12 12 12 12. Okay, so that is, 0 skew or some 0.1 skew, that's fine. Skew up to, some 4% is okay. Okay, I mean, generally we cannot say that 4 means you will have always data in 4 multiples, nothing like that, right? Data will be like anything. So, I mean, up to, after distributing evenly, there will be extra records will be there in some slices. Like 100 records, we have 12, 12, 12, 12, plus first 4 slices have, one record extra, like 13, 13, 13, 13. So that is always, so that will not be much skew. Okay, but if this is something like 75, 5, 5, 5, 5, this is, high skew. So what is this skew? Uneven distribution of data across slices is called skew. And this skew will lead to poor performance. So in distributed system, you will have better performance when you have less skew or 0 skew. 0 means what? If it is evenly distributed, it is 0 skew, or evenly is not all the time possible. So something like, a few records extra in some slices also, that's fine. Okay, but skew up to some 4% is also fine. Okay, the more, so that's why we say the more evenly distributed, that much performance you will have. The more unevenly distributed, that much skew will have, that much performance issues you will have. Okay, so now when will the data will be distributed unevenly? That is the next question. Okay, so this will be discussed, I mean, this is a separate concept that will be discussed as a table distribution or table design in Redshift. Okay, table design in Redshift. Okay, because we saw that if you don't evenly distribute, it's of no use, obviously, right? I mean, this can be, you see, this can be explained very simple technique. You see, you are going to movie theater, right? Movie theater. In movie theater, you will have, some 10 rupees tickets, 20 rupees tickets, 50 rupees tickets, 100 rupees tickets, and let's say 200 rupees tickets. Total five classes: 10, 20, 50, 100, 200. Why they put that many? I mean, in fact, you will have 5 different doors. Why 5? You will have, 2 doors for each class. For 10 rupees also, you will have a door from this side and that side. And for 20 rupees also, you will have a door from this side and that side. And from 50 rupees also, you will door from this side and that side. Similarly, 100, 200. So total, how many doors? You'll have 10 doors. You have 5 classes of fare, 10 doors. Okay. So that is for parallelism. People can go from both sides and come from both sides. Let's say, although you have 10 doors, but let's say people are coming only from one door, then how much time it will take to vacate the entire hall of maybe 500 or some 400 people of cinema hall? It will take a lot of time, right? If 400 people has to exit from single door, same thing here also. Although you have, okay, multiple slices, if it is not distributed and it is all lying in one slice and it has to retrieve from the same slice, it will take a lot of time. then what is the use of having all other doors? No use. Okay. So at most care should be taken care how evenly you will distribute the data. So the more evenly distribute, that much performance you will have. The more unevenly distribute, okay, that much skew you will have, that much performance issue it is. Okay, cool. So then how do we distribute the data, or how does Redshift will distribute the data properly? Okay, so that will be discussed in table design. Okay, Redshift table design. Okay, so that we will see tomorrow. Any questions? Hello, Somnath or Prasad, any questions?
No, sir, yeah, got it.
Okay. I think if you have no questions, then we can meet tomorrow, same time.
Yes, sir. So tomorrow we'll be discussing on the distribution related concepts, right? Like how Redshift does.
Tomorrow we'll be distributing, the columnar. Yeah, I mean, daily there will be some subtopic will be covered. Okay, so this columnar, like, what is this columnar storage? Okay, columnar storage followed by distribution keys. Okay,
Okay. Got it.
yeah. Okay, yeah, some supporting concept followed by the main concept. Okay,
Yes, sir, yeah, it's okay. Thank you.
okay, cool.
Sir,
Yeah, tell me.
the you not evenly distributed the means క్యూస్ అంటున్నారు కదా సార్, దీన్ని ఎలా ఓవర్కమ్ చేస్తాం సార్ మరి?
మరి అదే కదా రేపు చెప్తాను అంటున్నాను.
ఓకే.
ఓకేనా? Yeah, for what why it is leading to skew is unevenly distribution of data. So why it's unevenly distributing, or why it is causing as uneven distribution, and how to avoid it. Okay, we'll be seeing tomorrow. Or what is that leading for uneven distribution of data and how to overcome it.
ఓకే సార్.
Okay.
ఓకే.
Yeah. If possible, you can also read and come. Let's see if you know some points. Otherwise, don't worry. These are very key points. So I'll be telling you tomorrow.
Yes, sir. Yeah. Thank you.
Okay, then. See you tomorrow. Take care.
Yes, sir.